Dear students, let's see phase diagram of water. So, as you know, this line, this line from A to E, this line represents the liquid vapor interface, or you can say evaporation line, and this is solid liquid. So, this region is basically this is solid. So this is a solid region, means H2O. Solid means ice, you can say, and this is liquid, and this is vapor region, right? So this region is vapor, this is liquid, and this is solid in the phase diagram. And this point A is critical point, as all of you are knowing that all three phases merge together here and coexist, means three equilibrium. So point A you can represent like this, that H2O solid, H2O liquid, and H2O vapor or gas, you can say. All three phases are in equilibrium. Right? So all three phases coexist. This is at the point A, and you know this is known as triple point. Triple point. And at this triple point, T and P are fixed at C. It is given 0.01, and this is this is 273.15, so this is 273.16. so for water it is 273.16 Kelvin. This is degree Celsius, so it is a okay 0.01 it is given, and pressure is 0.006 atm. 0.006 atm, right? I think before also this I have written some 0.006 bar, and here 0.006 atm. Okay, see this line, this solid liquid line is tilting towards this y-axis. So what you can say, what I have explained you, that the density of this ice or solid, you can say solid water, this is less than density of liquid water. This is abnormal behavior of water, you can say abnormal behavior, abnormal behavior of water, right? So all these things we have already discussed. This is triple point. See, this triple point for water is at this degree Celsius 373.99, and this is the critical pressure for water. And you know how critical point is defined. Beyond critical point means at after critical point liquid and vapor phases merge together and whole system exists as a single phase, right? Now see here, this is 1 atm pressure. This is 1 atm pressure, and corresponding to this, you take this 1 atm pressure and make one line like this. So this intersecting at this point. Here B on the solid liquid equilibrium, and liquid vapor it is intersecting at C. So point B is here. B point is normal freezing point. Normal freezing point of water. Why I am not telling this standard freezing point of water? I have written here normal freezing point of water. You know, when you take pressure 1 atm, then it is called normal. Remember this point. When the pressure is 1 atm, then it is called normal, and when the pressure is 1 bar, then it is called standard, right? So B is the normal freezing point of water, and C point is the normal boiling point of water. Point C. So whatever temperature and pressure corresponding to that, they are, I mean, responsible, and they are the characteristic for this liquid. So C is the normal boiling point. Normal boiling point of water, right? So from here you can define what is the boiling point and what is freezing point. You can very easily define it, right? How? See, that's why I have started this graph basically, and it is very important point. And you know, when you increase the pressure, suppose that you have taken any point here. So here, if you take, if you draw the line, then at this pressure, this is the, I mean, what? Freezing point. This is not the normal freezing point, but this is the freezing point of water. Means what is the effect of pressure on the freezing point? And now this line will increase from here to here and make this point. So at any point where this, I mean, that line intersects this line, that represents the boiling point of water. So from this graph you can very easily explain, with rise in pressure, the boiling point will increase but freezing point of water decrease. And if this line is straight parallel to this, means there is no effect of pressure on the boiling freezing point of that material. And if this line is like this, then what will happen? With increase in pressure, freezing point as well as what, boiling point, both increase. So from this graph you can very easily understood how this pressure and I mean pressure basically, because we always define this boiling point and freezing point at pressure. We are taking fixed point here, then we will find the point here. We are not taking the fixed point on the temperature and then find the pressure, what is the pressure. So every time when you are going to define freezing point or boiling point, so first you have to fix the pressure. After that you have to find the temperature corresponding to that pressure which is responsible, right? So from this expression, this phase diagram of water, suppose that if you are studying the vapor pressure of any solution, so this graph is still valid there also, because this you can use as a reference graph, and then with respect to this, this is a pure water, so you can use this graph to compare the behavior of water in solution. How this behavior of water changes when you are putting some solute in the solution, I mean to make the solution, right? So first one by one we can define. So what is the freezing point? See how to define this normal freezing point. So for this definition of this, we can make definition from here. See here, in a solid liquid equilibrium. So first you have to make the solid liquid equilibrium, and see the temperature. make the definition: temperature at which solid and liquid equilibrium coexist at 1 atm pressure. You know, throughout this line, solid and liquid are coexisting with each other, but not every temperature is called not freezing point or melting point. So we have to make some standard for this, because this whole line is expressing the solid liquid interface, solid liquid coexistence line. This is, so the reference is pressure. So if at any point of time, if someone asks you, okay, tell me this freezing point or boiling point or melting point is defined with respect to which variable, so your answer is pressure. Pressure is important. So normal freezing point, the temperature, we can make a definition: temperature at which the chemical potential of solid is equal to the chemical potential of liquid, right, at 1 atm pressure. At 1 atm pressure for solid liquid equilibrium. Solid liquid equilibrium, right? So this definition you can make, that the temperature at which this chemical potential of solid and chemical potential of liquid is equal at 1 atm pressure for this equilibrium. You know, this if the chemical potential of solid and liquid is equal, means both are in equilibrium condition. So this is the condition for equilibrium. So this is the perfect definition of freezing point. Or if you do not want to include the name of chemical potential, so you can write temperature at which solid liquid coexist. Solid liquid equilibrium means solid and liquid coexist under equilibrium at 1 atm pressure. You can make this definition also, no problem. So if you do not wish to use this chemical, the word chemical potential, so you can write this definition: or temperature at which at which solid liquid coexist at 1 atm pressure. So the definition includes this key point: 1 atm. Temperature is not, temperature maybe increase, maybe decrease, right? So but both the variables are important, not only one variable, but definition is made with respect to this 1 atm. Similarly, we can define this normal boiling. So for water, what is this? For water at 1 atm, what temperature we are getting? The temperature is this 00, so 273.15 Kelvin. So for water, the freezing point TF for water is equal to 273.15 Kelvin or 0 degrees Celsius, right? Because at this temperature and 1 atm pressure, this solid liquid equilibrium coexist, right? Solid liquid equilibrium coexist. Similarly, you can define normal boiling point. Normal boiling point. Normal boiling point. So similar definition you can make for this also. Normal boiling point normal boiling point. So normal boiling point you can write here the definition that the temperature at which temperature at which liquid vapor equilibrium liquid vapor equilibrium liquid vapor equilibrium coexist at 1 atm pressure. Or you can write that this H2O liquid to H2O vapor, this equilibrium, right? H2O liquid to H2O vapor, and you can write here that the mu of liquid is equal to the mu of vapor. So this is the thermodynamic condition for this. So for water, this boiling point of water TB is equal to 373.15 Kelvin or 100 degrees Celsius. So this is called normal boiling point of water. This is not standard boiling point. When this is called standard boiling point, when you change this 1 atm with 1 bar, right? So when pressure is 1 bar, then freezing point is known as freezing point, normal freezing point. Then when 1 bar, then normal freezing point is known as standard freezing point. Known as standard freezing point, right? And then normal boiling point is known as standard boiling point. Standard boiling point, right? And all of you are knowing what is the relation between 1 atm and 1 bar. See, 1 atm is equal to 1.01325 bar. So this is the relation. So 1 atm is equal to this bar. So this is I mean the definition of normal boiling point or boiling point, normal freezing point or freezing point, and this standard freezing point and boiling point. Now see what factors affecting the this boiling point and freezing point depends on the following factors. See, boiling point and freezing point depends on the following factors. Right? So boiling point and freezing point depends on the following factors. What are those factors? See, boiling point and freezing point depends on the following factors. First factor is the nature of matter. Right? Nature of the matter. More precisely, you can say nature of matter means intermolecular forces. Intermolecular forces. Second factor is the temperature. Second factor is the pressure. So if you change the pressure, not temperature, if you change the pressure, then the freezing point and boiling point will change, right? So mainly on two factors this depends, boiling point and freezing point, pressure and more precisely you can say vapor pressure. See, this pressure you can say this is which pressure is this? This is external pressure, you can say external pressure. Right? So this external pressure, if you change the external pressure of any system, then this boiling point and freezing point will change, and the nature of liquid, right? So see, this boiling point and freezing point depends on mainly these two factors. Don't write here temperature. Why? Why we are not considering here temperature as a variable for this boiling point and freezing point? Because we are selecting pressure as a standard pressure, so on changing pressure, temperature will automatically will change, right? So this external pressure and this nature of matter, these two are important factors which on which this boiling point and freezing point depends. We have not made the temperature as a reference for this. So pressure, we should make the pressure fix, and then accordingly temperature will change for different matter, right? If you take water, if you take ethyl alcohol, if you take any other matter, so this boiling temperature or freezing temperature will change accordingly. See, here if you study this graph, so here this is external pressure. If we assume this is an external pressure and this is the temperature, so if we increase the external pressure, so can you tell me any daily life phenomena in which the external pressure is increased? So the answer is pressure cooker. In pressure cooker, with the putting that lid over the cooker, that lid exerts the extra pressure on the surface, right? So if you increase the external pressure, means if you are putting a lid on the if you take open container, so in open container the external pressure is 1 atm, but if you close that container, you are increasing the external pressure. So in pressure cooker, boiling point will increase. See, if you increase the pressure at any point, if you can take suppose that I am taking here this at this point, suppose that this is 2 atm. So if we I will put a line here, so this line intersects here, this line, so this you can make here, and now see the boiling temperature changes, boiling point changes, and here if you see the freezing point will decrease. So see, at this point the freezing point will decrease. So what we can generalize here, that if we increase the pressure, increase in pressure, case 1, if pressure is increased, so if the pressure is increased, the freezing point of water decrease, and boiling point of water increase, right? So if you increase the external pressure, which pressure? External pressure. This pressure is the external pressure. So if you increase the external pressure over a liquid, so the boiling point will increase and freezing point of water. Every time I am mentioning this water. So freezing point of water will decrease, as you can very easily see from the graph, right? And so this case, pressure increase case, is exists in which system? Normal system, pressure cooker. So in pressure cooker, the external pressure is increased. The external pressure is increased due to the lid, closing of lid, and due to this boiling point of water inside the system, that will increase. And what is the consequence of this? If boiling point is increased, means you are putting more energy to the system for boiling, means, and at boiling state the temperature is same, so that is a constant temperature phenomena. So once water starts boiling, there is no change in the temperature. So whatever energy you are giving from outside to the system, that will convert the liquid into vapor. That will not increase the temperature. So in this situation, whatever energy you are giving, if boiling point is more, means you are putting more energy to that system. So more energy that system means the cooking time for the food, that will decrease. So why cooking time is reduced in pressure cooker? Due to increase in pressure, boiling point will increase. Boiling point will increase means we are putting more energy at equilibrium, and more energy at equilibrium means lesser time to cook the food, right? Similarly, if you decrease the pressure, if external pressure is decreased, then freezing point of water will increase, and boiling point of water decrease. So what is the case of this case? Normal case, at the height from the sea level, if you move on the higher altitude, then what will happen? Pressure will decrease. Pressure will decrease means the boiling point of water will decrease. Now water start boiling below 100 degrees Celsius. So what will happen in this situation? In this situation, your cooking time will increase. So this situation exists in pressure cooker, and this situation exists in mountains or higher altitude, or at higher altitude. Right? So at higher altitude or at mountains, the external pressure will drop. External pressure drops means boiling point drop and freezing point rise, right? So this is the reason why you are getting more ice on mountains, not on the plains, because freezing point increase, so the condensed point, you can say, increase. So at higher temperature you get the ice, right? So this can be very easily explained on the basis with the help of this phase diagram of water. Everything is clear, and if you know the concept that this boiling point and freezing point This is defined at 1 bar pressure at constant pressure, not at constant temperature. It may be temperature, maybe could be anything, but the pressure should be fixed. So this normal freezing point, normal boiling point are defined at 1 atm pressure. Standard freezing point, standard boiling point is defined at 1 bar pressure. And how this pressure, increase or decrease in the external pressure affects the boiling point and freezing point of water. But see, this is I have argumented here for water only. You cannot see this as a normal, as a general case that will be applicable for every liquid or for every matter, right? For every matter, you have to find this first this phase diagram. After that, you can say anything. With the help of this, you can explain anything, because if this line is like this, so you cannot say that on increasing pressure the melting point will decrease, right? That you cannot say. So this is all about the phase change, phase equilibrium, and factors affecting this phase. We have two main factors, temperature and pressure. So this boiling and freezing phenomena, this is defined with respect to pressure, not with respect to temperature. That's why I have not included here temperature as a variable for freezing point and boiling point, because this boiling point, it is not defined with respect to temperature. So freezing point and boiling point, that we cannot say directly depends on temperature, but they depends on pressure. If you change the pressure, then the temperature accordingly will change, right? So this you can say, on the basis of this phase diagram of water, and this is very general diagram and very helpful in this chapter in future, right? Well, see this question. Let's do practice one question here. The question is, determine whether the chemical potential of two phases listed are the same or different. If they are different, state which one is lower than other, right? So first case, it is given A, liquid mercury. So whatsoever it is given, you can write as mercury liquid and mercury solid at its normal melting point. So melting point, if it is asked, so it is better to write here solid, put the reversible reaction arrow, Hg liquid, because here left to right this representation expresses the melting, and normal melting point means pressure is 1 atm. Pressure is 1 atm, and they have given the melting point. So Tm is given, melting point is given minus 38.9 degrees Celsius, right? So at 1 atm, how we have defined here boiling point, freezing point, or melting point. Freezing point and melting point both were same, but only the direction is different. See, it is defined at 1 atm, so this represents the equilibrium condition. So basically, from this data, we have concluded that this system is under equilibrium from this data. So this is under equilibrium. At equilibrium, therefore mu of mercury solid is equal to mu of mercury liquid. means the chemical potential is equal for both, right? Means Gibbs energy per mole, it is equal, not Gibbs energy of whole system, Gibbs energy per mole, it is equal. Okay, hopefully all of you are clear. Second point, second case, it is given B. What is given? H2O liquid or H2O gas at 99 degrees Celsius and 1 atm, right? So H2O liquid and or H2O gas H2O gas H2O gas at 1 atm at 1 atm and 99 degrees Celsius. 99 degrees Celsius. Is this equilibrium condition? First you have to decide whether this is equilibrium condition. The answer is no. Is this equilibrium condition? Equilibrium condition. First you have to decide whether they are under equilibrium or not. Is this equilibrium condition? The answer is no. The answer is no. So if this is not equilibrium condition for water, then what will happen? Chemical potentials are not equal. So in this situation, which phase is more stable? Suppose that it is asked that, okay, tell me at 1 atm and 99 degrees Celsius, which phase will exist? Because both the phases will not coexist. So see, this is 1 atm and this is 100. So 99 would be something here, 99. So if you match this, point from here to here, so you will find at this point. So this point belongs to the liquid region of this. Means your matter exists in the liquid phase, and the meaning of that, the chemical potential, your matter exists in the liquid phase, means H2O liquid phase will be there. I mean, if you have taken some quantity, so maximum quantity of that matter will exist in liquid phase. So you can say under this situation, chemical potential of gas H2O is more than the chemical potential of water liquid. So at this situation, at this condition, more and more vapor will convert into the liquid. Chemical potential of water vapor is, if you have taken water vapors and water liquid together, so in this situation at 99 degrees Celsius, more and more tendency of vapor to convert into liquid. So the chemical potential of water gaseous is more than the chemical potential of water liquid. This is very good case and very important case. See, C part is given H2O liquid or H2O gas at 100 degrees Celsius and 1 atm. So H2O liquid and H2O. So here which kind of arrow you can put? Here you can put arrow like this. You can put arrow like this here, that like this, right? This is not the, you cannot say that system is under equilibrium, and do this, remove this arrow and put this kind of arrow, right? Okay. H2O liquid and H2O gas at 1 atm, at 1 atm and 100 degrees Celsius. So this is equilibrium condition. Equilibrium condition, right? So in this situation, you can say mu of this H2O liquid is equal to the mu of H2O gas, right? This is gas. So which kind of arrow you can put here? You can put this type of arrow, right? So in this situation, there is a equilibrium condition. So chemical potential of both the phases is equal. One more part is given, D part C. What is this? H2O liquid and H2O gas, H2O liquid and H2O gas at 1 atm and 101 degrees Celsius. So this is again non-equilibrium condition, non-equilibrium condition, right? So, and you know, at this temperature, if you see your phase diagram, so 101 degrees Celsius lies something here, and if you extend the point like this, so this 1 atm line will intersect somehow here at this point, at this point, and this point belongs to which phase? This is completely vapor phase. So means at this 101 degrees Celsius, vapor phase is more stable. So the you can say that the chemical potential of H2O liquid is more than the chemical potential of H2O gas, right? So which kind of arrow you can put here? You can put this type of arrow here, right? Very good. Now see another question, D part. Now E, solid lithium chloride or gaseous lithium chloride. See, solid lithium chloride means LiCl solid or LiCl gas at normal pressure means 1 atm and 2000 degrees Celsius. At 1 atm and 2000 degrees Celsius, right? And one more data is given here. The boiling point of lithium chloride is 1350. The boiling point of lithium chloride is 1350. So first you have to tell that this 2000 degrees Celsius temperature, this and 1 atm pressure, this is equilibrium condition or non-equilibrium condition? So definitely it is non-equilibrium condition. Non-equilibrium condition. So if this is non-equilibrium condition and this 2000 degrees Celsius temperature is what? Much higher temperature than its boiling point. So obviously vapor phase is dominating here, and if vapor phase is dominating means you can say the mu of lithium chloride solid, mu of lithium chloride solid is more than the mu of lithium chloride gas, right? Lithium chloride. So which kind of arrow you are putting here? You can put this arrow. Means more and more lithium chloride solid will be sublimating into the lithium chloride gas. I mean, liquid phase may or may not exist. That is not mandatory here. But solid and gas, this sublimation. So this sublimation is a spontaneous phenomena, and this will convert into this, right? So this is spontaneous. This is also spontaneous. This is also spontaneous, right? But this is equilibrium, under equilibrium condition, right? So this is the way how to explain this chemical potential and what is the application of chemical potential. Hopefully all of you well understood that phase transition and stability of any phase is determined and controlled by chemical potential, a thermodynamic function, also known as Gibbs energy per mole, right? So this will control everything regarding phase transition and phase coexistence and stability of any phase, right? So